Okay.
Do like your Lisa Simpson diagram, I must say.
Yeah, we've been debating what the spacecraft design is going to look like. I like your solution if we can afford the copyright. All right, it is 1/4 the hour. Welcome back to session B1 on astrophysics of LISA. We have a couple talks scheduled for this half of the session. We do have a slight change in the program. The first speaker is unable to make it, so we're going to push the second and third speakers up a notch each and get started with Roberto Cotesta speaking on Bayesian parameter estimation of massive black hole binaries using an in-spiral merger ring-down waveform model with higher modes. So Roberto, please take it away whenever you're ready.
Thank you for the introduction and for letting me present this work at the LISA Symposium. I am a postdoc at Johns Hopkins University, and I'm going to discuss this work that I've been doing with my collaborators that I've written here. And as I said, I'm talking about Bayesian parameter estimation of massive black holes using in-spiral merging down waveform models with higher harmonics. So let me explain a bit the goal of the study. So I'm sure that everybody is familiar with this plot here. Here we are showing the SNR as a function of the total mass and redshift for massive black holes. And basically the color is the SNR of the system at that total mass and redshift, and the number on the plot is the expected SNR. And what we want to focus on in particular are the system under this magnified lens that have that are the golden Lisa binary, which are those with the largest SNRs. We are interested in those, of course, for several reasons, and we want to understand how well, in particular, we want to understand how well we can measure their masses and spin to constrain the formation scenario, and also to understand how well we can skylocalize them for multi-message follow-up. And this is also, in this case, there's some overlap with the other presentation that Silvan made before, and in fact, he's an author of this paper as well. Okay, so let me tell you what's the method that we use to do this study, and I apologize for the long text in this slide. I'm making sure that this is the only one on this slide with all this text. So to do that, we create a set of 4,000 synthetic signals emitted by massive black holes, and we draw them. So in principle, we could have used like a population, a theory-driven population. But since there's a lot of uncertainty on the population of massive black holes out there, we prefer to do a more agnostic study and scanning around the parameter space. So we pick the parameters of our massive black hole binaries in the most agnostic way we could do. So we choose for example, the redshifted total mass of the system to be log uniform distributed in the range 10 to the 5, 10 to the 8 solar masses. We picked a uniform distribution for the mass ratio between 0.1 and 1. We consider only spins aligned with the orbital angular momentum of the binary, and we pick them uniform between this component uniform between -1 and 1. We draw distance uniform in comoving volume, considering the redshift range 0.53, and we restrict ourselves to signal lasting for 1 year or less in this. Using this population, we perform Bayesian parameter estimation on all the 11 parameters of big radiation wave signal using the code Lisa beta that Silvan described in his presentation before. And we also use the waveform model, the in-spiral measuring that waveform model, IM alpha and HM, that includes the higher modes. And for people who are not familiar with higher modes, just like a very short description, higher modes of what higher modes are. So when you decompose the strain in H plus minus H cross, you have this decomposition in spin-weighted spherical harmonics that are this function here. And usually a common approximation is to only use the L equal M equal 2 to approximate the signal. But this is actually not a very good approximation for many signals. And so and this was known already in the past. And in fact, we are using also modes that are beyond the 2-2 mode alone. So the idea to this study is to give an update on top of past studies that had different approximation. For example, some of them didn't use the full inspiral measuring down waveform. Some of them didn't use Bayesian parameter estimation, but only use Fisher matrix. Some of them only consider few systems instead of doing a scan on a parameter space. Okay, so let's go a bit into the detail of the population, not the population, sorry, the set of binaries we choose. And so here in the left panel, in the left plot, I'm showing the SNR distribution of the massive binary that I'm considering, and I'm showing the total SNR, that is the histogram in black. And you see that the median SNR for the system is about 10 to the 3. And this is more or less corresponding to the SNR of the Tutu mode. You can see that the blue dash histogram is more or less on top of that. But I also show the SNR continent in the other harmonics, and you can see that they are not negligible. For some of them, they have SNR medians of around 10 to the 2. So this means that even if the contribution is subdominant, it's still large enough to be important for the signal. On the right panel, I want to show instead the effect of the inspiral measuring down waveform on the signal, and in particular on the SNR of the signal. This is also in line of what Sylvain discussed before. And in this plot, this is again a plot of all the binaries. Basically, each point in this plot, in this scatter plot, is one of the 4,000 systems we consider. So as a function of the total mass and the redshift. And the color code is representing the impact of the SNR in the measuring down over the SNR of the full signal. And I define the measuring down as starting from the frequency that is the frequency of the Schwarzschild ISCO, that is this frequency here, as it's commonly done in literature. So you can see in this plot that the black points are those for which the measuring down is not that important for the full signal. In fact, its contribution to the SNR is more than 10%. And this is true for binaries around 10 to the 5 solar masses, but you can see that the more you go to higher solar masses, and in particular starting around 10 to the 6 solar masses, the more the measure is important. At some point is the dominant part, as you can see in the red dots. Okay, now let's go to the results. I think it's useful to give an introduction to this kind of plots because you will see many of them. So let me introduce them. So here I'm showing the uncertainty on the detector frame mass M1Z as a function of Z and MZ, the redshift and the shifted total mass. And here in this kind of plots, I will always show the uncertainty in color as a function of the parameter that mostly control that uncertainty. So if you don't see the other parameters here, for example, psi, is because this uncertainty on the detector frame mass does not depend much on psi. So in each of these plots, each point again is a binary, one of the 4,000 binaries that we consider. We show, so the color is a 2 sigma uncertainty. And here you see 3 colors. I always use 3 colors. The red is the best, the best measured binary that are the most interesting, of course, and the black being the worst measured binary that are the less interesting. So I also have these curves that are to guide the eye, and they include 50% of the system inside the color category to give an understanding. So now let me actually describing what I'm showing in this plot and not in this generic kind of plots. Here, as I said before, I'm describing the uncertainty on the redshifted mass of the primary, and I will only show the primary because exactly the same trend is true also for the secondary. And what I want you to focus, because I think it's the most interesting stuff, is this red region, the region with the red plots, and is where we measure best the mass of the primary with an uncertainty that is smaller than 10 to the minus 3. And this is basically in this region that I say here between 2 times 10 to the 6 and 2 times 10 to the 7 solar masses for H is smaller than 1.5. And this is just completely due to the SNR. In fact, if I overplot the system for which you have the biggest SNR, they are exactly those. So this is not super interesting, but let's go now to the interesting stuff. So this is the source frame mass, which is the most interesting part for the astrophysicists, because this is what they want to know, not the detector frame mass. And namely, this depends not only on Z and MZ that control the SNR, but also on the inclination angle. And in fact, because of the redshift dependence. And in fact, I can tell you that actually the trend almost perfectly follow the trend of the uncertainty on the redshift, because the redshift is way worse measured compared to the detector frame mass. So the uncertainty on the source frame mass is completely dominated by the uncertainty on the redshift. Again, so here I'm showing the uncertainty for the primary, the same is true for the secondary. And again, here I'm showing as a function of mz, the redshifted total mass of the system and the redshift, but also the inclination angle, that is the inclination angle at which the observer see the binary in the source frame, and with respect to the orbital angular momentum of the binary. Again, there's this the smallest uncertainty that is smaller than 10 to the minus 2 is in the MZ plane, is in the region where you have the largest SNR. But I want to highlight the other dependence, the dependence on the inclination angle. In fact, you see that you best measure the system that are either face on with cosine iota equal 1 or face off with cosine iota equals -1. And this is also kindly half due to the SNR, because of course there the SNR is larger, but the ratio between the SNR face on and face off is about 2, but here you change when face on and John is about 2, but here you change the uncertainty by 1 of the magnitude. So it's not only the SNR, but it's also the fact that the likelihood changes more when you are closer to face on and face off, and that's why there you measure best the parameter. Let's move on to the spin. Here I show the uncertainty on the spin of the primary as a function again of the Z and MZ and the shifted mass, and the other two parameters that are important here are the mass ratio and the spin. So we have a bigger corner plots. Okay, let's start discussing breaking down this corner plot. So again, we have the effect of the SNR. This is the region where the spin is best measured. The spin of the primary is best measured. Is where is measured at best than 10 to the minus 2 is again the region with the largest SNR, and we knew in the MZ plane, and this is expected. Also,
Roberto, you have about 2 minutes just for planning.
Yes, thank you. And also the SNR is largest when we have larger spins. So basically, we best measure the spins of we best measure the spins when the spins are large. This is more interesting, and is when we best measure the spin when the system doesn't have comparable mass, but is away to comparable mass. In fact, you see that you can measure the spin further away at a further away redshift when the more the mass ratio is small. And this is due to higher harmonics, because they are more excited when mass ratio is smaller, and so you can measure best the mass ratio, and since the mass ratio is correlated with the chi effective, if you can best measure the mass ratio, you can best measure the spin. I'm not showing the chi2 because the trend is similar. Finally, I want to talk about the sky area. This is stuff that also Sylvain has discussed, so I'm going to be fast. Again, here we have that, yes, there is an effect of the SNR in the MZZ plane. You can see that the best measured system with an uncertainty of smaller than 0.1 squared degrees when the SNR is largest. But the most important dependency is what Sylvain was discussing as well before, the declination angle that is defined as here. The declination angle is with respect to the LISA reference system at merger, and the inclination of the binary. And in fact, you see that this is a very good predictor of how well you can measure the sky position of the system. And yes, I will leave you with the conclusion that basically we updated the Bayesian parameter estimation uncertainty for the Gordon binaries for all the relevant parameters. And here I'm just leaving basically the same bounds that I said before. And I also want to tell you about some future work that, because we have been talking about the uncertainty I've been talking about are statistical uncertainty that are actually very small, but we do expect that systematic uncertainty are going to be actually very important. And in particular, we want to understand how much the waveform models systematics are going to be important, and how good waveform we need to not let them be important. Thank you.
All right. Thank you, Roberto, and thank you for sticking to time. We do have time for a couple questions. I have not seen any questions in the chat yet. I don't know if there's any questions on the YouTube. Rona, do you have any questions from the YouTube live stream?
So far, no questions,
So far,
but
no.
we have viewers on YouTube, so if they do have questions, I can pass them along.
Okay.
Okay, I'll stop sharing.
Actually, well, not quite yet. If you can go back a slide and give people an opportunity to type something, and I'm going to ask a question.
Yeah.
Maybe go back this one here. So if I could try to understand this, you're saying that obviously there's an effect on this, I forget what you called it, sort of a declination angle in the frame of the detector.
Yeah.
There's an SNR effect there, but you're saying here there's more than just an SNR effect. It's
Yes.
something to do with the likelihood surface gets steeper as you get towards those extremes on that angle, the cosine of that angle.
Yeah, actually, if you Silvano also showed that, because the SNR is not largest in this region.
Right, it's the other way.
Yes, yeah. And that's exactly true also for the mass ratio, like for the spins. Like when you look at the measurability of the spin here, right? You don't expect, so actually the mass ratio, the SNR decreases with smaller mass ratio. I don't know why this thing is so slow. Yeah, decreases with smaller mass ratio. But because of this effect, actually you measure best the spin when you have smaller mass ratio, other than the larger, and for which this larger mass ratio you have the largest SNR. So also in that case, it's like counterintuitive if you only think about the SNR.
Okay, so we do have one question, and I'll read this one out, and then we can, after you answer this, we'll move over to the next speaker. It's from a Krishnendu. Could you say a bit more about the waveform systematics that you plan to do? Also, do you have a feeling about how the spin precession effects may change the conclusions?
Okay, so the waveform systematics, say more. We are just gonna see. Basically, the idea would be to understand which. So the mismatch is the measurement for how well two waveform agrees. And basically, we are going to trying to understand what is the mismatch that we need such that the systematic uncertainties are subdominant with respect to the statistical uncertainty. So we don't want the systematic to be a problem. For the precession, how much will it change? Well, I don't think it will change much for sky location. Maybe it will improve a bit the sky location based on the experience with LIGO. Because apparently precession can improve measuring the inclination angle, that can improve also measuring the sky position, I think. And of course we will have different results for the Chi-1 measurement. But honestly, I don't know on top of my head how much that will change the Chi-1.
All right, thank you.
No problem.
And Krishnendu, thanks to you as well. Right. So the second talk in this session was originally scheduled to be the third talk in this session. So we have advanced to the future. And can I ask Tom Wag to please bring up his slides? Great. Okay, we see them. So again, Tom Wag is going to speak about legwork, a Python package for computing the evolution and detectability of stellar origin gravitational wave sources with space-based detectors. Whenever you're ready, Tom, please take it away. Oh,
sorry, I forgot to unmute, so I had to switch.
aha, okay.
How's that?
It's great. I can see it and I can hear you.
Perfect. And yeah, apologies in advance that I'm on a tablet, not on a laptop. Aer Lingus lost my bag. That's life. So I'll do my best with that. But yeah, very excited to be talking here today. Thank you very much for having me. Talking about legwork. This is a Python package I've made with Katie Breivik, and Selma's done some supervision as well. And yeah, so what is it? So the idea is that you can kind of sit back and relax a bit and let us do the legwork for you. So legwork is the LISA Evolution Gravitational Wave Orbit Kit, convoluted acronym as ever. But it's a Python package that can evolve sources in terms of their orbital evolution. It can calculate gravitational wave strains, calculate SNRs, sensitivity curves, and then it visualizes the results as well if you'd like. And it should be super easy to install. All you have to do is pip install legwork. So hopefully you're now intrigued, and I can give you a bit of outline of what we're going to do. So what I'm going to be talking about is a bit about the motivation behind legwork, why we think it's a good idea for it to exist. And then once you're all excited about it, we can talk a bit about what it can do, some of its capabilities. And in kind of line with that, show some example use cases of just some things you might, have as a demo of things you could do with it. And finally, I'm going to give you a little bit of a sneak peek of Legwork Online, which is an online interface that I'm very nearly done with, which should hopefully make it even easier to do things like this. So,
hi, Tom. Sorry to interrupt. Is your camera intentionally off?
Sorry, I should have said this while I'm on the tablet. For some reason, if I share screen, it turns my video off. Don't know why. Couldn't work it out in the other session.
Don't worry. Carry on. Thank you.
Yeah, sorry about that. Yeah, so motivation. Why do we think this is a good plan? Well, there's lots of people who are going to be using something like this. So stellar origin millihertz gravitational wave sources have been investigated in the past. You've got, quite a few papers there in kind of past couple of years. But then in more recent years, there's a bunch. So there's a lot of kind of renewed interest in this. And as we get closer and closer to LISA, you can only imagine that this is going to get more. And so lots of people are going to be trying to make exactly the same sort of thing. So we think it would be good to kind of have a central thing that everyone would work on. It's an open source package for the whole community. Every single paper that does this right now tries to kind of rederive a lot of the relevant equations. And this can sometimes lead to mistakes and very, very annoying factors of 2, which take very long time to work out. But we've kind of nailed this down and spent a long time thinking about this, and hopefully now have it right. And at the very least, it's open and everyone can see it and we can all work on it together. So the idea is that we can have experts collaborating, suggesting features, and avoiding doing all of that unnecessary work over and over and over again. And at the same time, what we can do is get newcomers to enter the field very easily and then quickly contribute to, all of the research that we do here. So hopefully now you're excited about legwork, and I can tell you a bit about, exactly what it would do. And before we even get to that, what I want to say is what you should, and perhaps more importantly, shouldn't use legwork for. So all of the equations that we're using in legwork only apply in this post-Newtonian approximation. And it's really quite a low order. It's like about order 0.5. And so this is great for stellar origin sources that are still inspiraling, absolutely fine for those. But for supermassive black holes, things like that, that's going to break this approximation. You don't want to be using legwork for that sort of thing. And legwork is designed for binaries. It can handle any sort of eccentric binary, that's fine. You can adapt it for triples or higher order systems as long as you know the frequency and eccentricity evolution. But it's not designed for something like a continuous gravitational wave source, which honestly I would not know what to do with. So that's not what legwork's for. And so there are a lot of equations that go into it, many papers. A lot of this has been kind of derived before, and we haven't really done anything new except put it all together in one place, and we've checked it really many times, and we've confirmed it against this, status paper, like the LISA document that derives the SNR, and we've checked that everything confirms with that, so we are happy that it is valid. If you want to read more about the equations, it's in section 3 of the paper, but I don't think anyone really wants to be reading equations right now. We want to see what it does instead. So what I'm just going to tell you is a bit about the structure of what the package is. It's built up of 7 different modules. I'm just going to give you a quick map of what they are. So first, we've got, your simple utility functions, things like that G and V function we saw before, just like the relative power in different harmonics, things like that. And that feeds into more important modules, such as the evolution module. This can do any sort of orbital evolution due to gravitational wave emission, and it can also calculate merger times. And that's fine for circular and eccentric systems. It can do both of those. And then that evolution can also be used with calculating, well, I'll get to that. So it can also calculate gravitational wave strains, both the regular strain amplitude and the characteristic strain amplitude. It will do both. And also we've got a module that handles power spectral densities. So all different sensitivity curves from LISA and Changqing and custom ones as well. And you can use all of these together to calculate signal to noise ratios. And finally, once you've got all your results, you might want to visualize them. And we've got lots of plotting routines that make this super easy to put them up on a sensitivity curve and things like that. And what we've then done is basically taken all of these and squished them all together into one Python class. So it makes it very accessible. You don't have to root around for different functions. You can just write something like get SNR and it will do it and handle all of the complicated bits in the background. Yeah. So let's just give you a couple of things that you might do with it. I think the most obvious one is just calculate signal to noise ratios of populations of sources. So you can rapidly do this for large populations. It will do different approximations based on whether you can assume it's stationary or assume it's circular. And it will only use a certain number of harmonics based on what you set the tolerances to be. So it's flexible, but it's as fast as it can be based on your personal choices. And then once you've calculated all of the signal to noise ratios of all your sources, you can then plot them quite easily. So if you want to make a plot like this, where you have a density distribution of your sources, it's just one line of code. Once you've calculated all your signal to noise ratios, you just say plot sources on sensitivity curve, and you get something like this. And so you can see we've got a density distribution here with some points that are just on the edges because you can't plot the full distribution, must be messy. And you can see, it's hovering for a couple of millihertz, and those are all of your detectable systems. And you can do something like that nice and easily. On the note of sensitivity curves, you can use lots of different ones. So here you can see we've got lots of different LISA curves, a Changqing curve as well. And so hopefully this makes it very convenient. There are an array of different settings. You can change the observation time of the mission. You can change whether you approximate the response function. You can also then change what detector you're using. Maybe you're using LISA. Maybe you're thinking maybe these sources are more suited to Changqing or something like that. And we also let you use a lot of different galactic confusion noise models. So we've got the one from the Robson paper, 2019, then also the Huang 2020, and the newer one by Sarah Thiel, 2021. That's actually being presented in Parallel Session D next, if you want to go take a look at that. And all of these you can use quite easily and quickly. But at the same time, say you've got some power spectral density function or confusion noise function that you want to use and it's not used by everyone else, you can experiment with these and use an entirely custom function if you want, and that should hopefully be very easy to do. If you can write the function in Python, you can then hand it straight to legwork and it will do its magic. And then other thing it can do is compute all of the orbital evolution. So what you can do is then use our parallelized precompiled functions and do this nice and quickly and efficiently for your large populations. So what you can see on this plot is a grid of sources that are spaced out in log orbital frequency and eccentricity. And I've just evolved them all for the same amount of time in legwork. I think I did like 1,000,000 years or something. And so you can see the ones with low frequency, low eccentricity in the bottom left corner don't really move. And then as you get to higher frequency, higher eccentricity, they evolve more and more. And you end up with the blue dots, which are the ones that have merged before that time has passed. And so that's an example of how you could do this orbital evolution. And so let's, talking of examples, see some example use cases of legwork, some things that you might want to do with it. So first of all, here's a plot where I tried to calculate some horizon distances. So what I'm talking about with the horizon distance is just the maximum distance at which a source is still detectable. And so what I've done here is got a grid of sources. All of them are circular, just to make my life a little easier with visualizing it. And on the x-axis, you've got orbital frequency. So on the left, you've got low frequency, things that are far away from merging. On the right, you've got high frequency, things that are closer to merging. And on the y-axis, you've got the chirp mass. So the bottom are low mass things, the top are higher mass things. And note that's a log scale as well. And what all these color contours are showing are those horizon distances. So you can see it starts out at like 1 parsec, but goes all the way up to a gigaparsec. So there's a large range here. And what we've done to try and guide your eye with this is add some typical masses to indicate distances at which these things could be detected. So you've got things like a double white dwarf with 0.6 plus 0.6 solar masses, but you've also got like a 10 plus 10 binary black hole up there. And at the same time, you can see these white contours where you've got some kind of typical galactic distances you might be interested in, like the Milky Way center or the Andromeda galaxy, or the nearest ground-based gravitational wave source, something like that. And so you can see you could use this, for instance, maybe you want to know, okay, at what frequency does my circular double white dwarf need to be in order to be detected in the center of the Milky Way? So it looks like on this, that's about 1 millihertz. And you can then kind of play around with this and do more things. And I think the one other thing to note on this plot is you can see there's kind of like a dramatic moment when you go past the merger time equaling the observation time. Everything above and right of that line, kind of the distances get much smaller, and that's because it merges before the emission is done, and so you kind of lose a lot of the signal buildup over time. So that's one example use. Perhaps also you'd like to see how the SNR of a source will evolve over time. And so what we've done here is taken a source that has equal mass ratio, both 15 solar masses. It's 20 kiloparsecs from us. And what I've got are 3 panels here showing the evolution of the eccentricity, the orbital frequency, and the signal to noise ratio. And what I'm showing you is how they evolve in the time before merger. So that 0 on the far right is the moment at which the binary merges, and then you've got kind of backwards in time in terms of megayears. And so you can see that as time goes on, the eccentricity goes down and it circularizes, the frequency goes up and it goes up dramatically towards the end. And you can see a similar sort of trend with the signal to noise ratio. And what you could use this for is perhaps say, at what moment does this source become detectable? So in this case, it looks like about 1 million years from when it merges, that signal to noise ratio pops above 7. And if we take that as a kind of fiducial detection threshold, that means that's the point at which that source would become detectable. So maybe you could use this to find out when different types of sources, like at what point would they become detectable? How close would they be to merging? Something like that.
You have about 3 minutes left.
Perfect. I think I'll be done early then. So third one is just to, or third and last example is for comparing different detectors. So say you've got a collection of sources and you don't know which detector you want to kind of focus on, you can maybe see which one would suit you better. And this doesn't have to be Lisa and Shanshin, it could be Lisa and Lisa with some other setting. But what we can do here is take a grid of systems with orbital frequency, again, same way as before, low frequencies on the left, high frequencies on the right. And this time the y-axis is showing you eccentricity. So you can see highly eccentric sources at the top and circular sources at the bottom. What I'm doing here is calculating the signal to noise ratio in both detectors using legwork. Oh, and I should say all of these systems have the same masses, same distances. But what I'm plotting is the ratio. So the gray dotted line is when they're equal, but you can see that kind of the circular kind of millihertz systems are much more detectable in Lisa, like 3 times more. Whereas Shanshin, if you get high frequency, high eccentricity systems, those ones are going to be more detectable because it kind of has that flat bottom at the right-hand side of that sensitivity curve. And so, yeah, as I'm saying, you can examine your biases in your different detector and maybe choose which one would be the favorite for your kind of potential population of sources. And so my final little sneak peek is for legwork online, which is something I was working on for no particular reason other than I thought it would be fun. And it's an online interface for legwork. So if perhaps you don't want to download a whole Python package, you can use a simple and convenient interface to legwork instead. And so what you can do is kind of do some quick calculations. The more complex analysis, you're still going to need the Python package. It's not quite as flexible because that was hard, but this is what you've got. You can input a single source. You can kind of plop in a whole CSV of sources if you just follow our format, or you can draw random sources from different distributions that we've got in there. And you can use different detector settings as you see, change the tolerances, and then you can do all of this kind of usual legwork things. So you can calculate signal to noise ratios, merger times, strains, you can evolve your population and make a bunch of plots as well. So all of that is there. And at the same time, you can then download all those results to a CSV straight afterwards. You'll get a big table at the bottom. You can click that download button in the top right, and you can do all of this without ever having to install a Python package. So I'm hoping that I can get this. I mean, it works on my local machine, so it's nearly there. I'm thinking like next 2 weeks, I'll hopefully be properly publishing it and giving links out everywhere. So watch out for that. So yeah, thank you for listening. As I said, let us do the legwork for you. And yeah, check out the paper, pip install it if you want. Documentation is legwork.readthedocs.io. Yeah, thank you for listening.
Thank you, Tom. Yeah, looks very exciting, very user-friendly. Let's see, we have a couple of chats, or a couple of questions in the chat. The first one is from our IT host, Rona McTeague. She says, this is amazing, I agree. Is it aimed at researchers, or could it also be used in education or training?
So I definitely think when I first did it, it was for research, but this online interface in particular, I think could be useful for education in that way. Because I think if you're going to do a full paper, you're going to want the Python package to get the full flexibility. But if you want to, get some people interested and say, what happens if I make the source this much more massive to the signal to noise ratio? I think that online interface could be very useful for kind of education in that way. I'd be excited to see it used that way, definitely.
I agree. Okay, second question from Karan Jani. Great talk. What are the waveform models that we can use in legwork?
So we don't use waveform models because we're not that fancy. We are just using just like the the stationary wave approximation, which I think. So So Karan, you clearly understand all of this far more than I do. But essentially, we're just using the equations that you'd find in Stas's document. So this is only for like the the lower frequency sources. And I honestly don't know too much about waveforms, which is why my answer perhaps sounds a bit rambly. But hopefully that answers your question.
Karan, feel free to jump in if you wanted to follow up.
Oh, this is great, Tom. And I think maybe we can take it offline. This is a great tool already, and maybe we can extend it for other purposes as well. Thanks.
Yeah.
I guess
I'd be very happy to talk more.
Maybe just as a final question here is about just sort of, I see you had the link there. Are some of the examples that you showed, do you have those available? Is that included if you download the package as a Jupyter notebook or however you did those?
Yes, they are all, you can see this, right?
Yes.
So if you just go to legwork.readthedocs.io, you'll see this. And we have a series of tutorials of various different things you might want to do, and also demos. So from my presentation, I stole a lot of them from here.
Right.
Like the comparing sensitivity curve ones here as well. All of the code is there for you to copy. A little copy button appears in the top right. So yeah.
Right. I'm familiar with this interface. This is a great interface for that kind of not quite power user, but which makes it a little bit easier. Okay.
Yeah, it's surprisingly easy to set up.
Yeah.
Hi, there's one more question from YouTube I've sent you.
I see that. Thank you for reminding me. So this is from a YouTube user, and it is the SNR computed using sky average sensitivity, or is the actual sky location and detector motion or orientation included?
Yeah, great question. It's sky averaged mainly. So you can do fully eccentric and fully evolving or chirping sources, however you want to say it, for all of the sky average. For the position specific, we only have it implemented for circular and stationary sources. So if your source is evolving or if it's eccentric, no, but if it is circular and stationary, yes, you can also put in the positions just using an AstroPy sky coord object. So yeah, and inclinations and polarizations too.
Very good. Okay, so before we adjourn, since we only have 2 of our 3 speakers for this session, I'll give people an opportunity to ask questions to any of the speakers. I believe we have our speakers still present from the first half of the session as well. And then I'll give people a few moments to put a question in the chat or raise their hand. Okay, well, I don't see any further questions. I think that's because the talks were all very clear. And that will conclude this session. And I think that also concludes the symposium for the day, at least this track of it. And I hope everybody is having a good time and learning a lot, meeting some new people, and will continue to do so the rest of the week. So thanks again to all the speakers. Thank you to our host. And thank you to all the organizers of the conference for putting this together. And we will see you during the rest of the week. Bye-bye.
Thank you, Ira. Bye, everyone.